Skinner. I'm the product manager for geotech products that we make at Oasis. And I'll let the others introduce you as they present later, with the exception of Carol, who is briefly here now. She's our leads the overall geotech team at Oasis, and she will be around later for any questions. So Shiva's currently sharing because he's first up. You jump onto the next slide, Shiva. We'll do a quick introduction to our current products. So as Oasis, as Alistair said, we make 3 core ranges of software. So for structural engineering, for geotech engineering, and also for pedestrian simulation. Inside our Geo suite, we have 9 products, and they're arranged in 3 groups, if you like. So at the top there, we have 2 products that cover piling. ALP looks at the lateral behavior of piles, whilst pile looks at the vertical capacity. Building damage assessment, XDisp, is sort of out there on their own, and you'll hear a lot more about that today. So that's, well, does what it says on the tin, how buildings are affected by settlements, sort of thing. And then at the bottom there, we've got 4 products that are more around ground movements. So Greta is for gravity retaining walls, Fru is for flexible retaining walls, so like a sheet pile, that sort of thing. Excavation, supported excavations. PDisp is for more general soil displacement analysis, and then slope is around the rotational analysis of slope, limit state analysis. So between them, hopefully that gives a good coverage of typical geotech design applications, analysis applications. And yeah, as we say, we're going to focus on the ground movement related ones today, particularly PDisp and XDisp. So next slide, Shiva, if that's all right. Go on to what we will cover today. So we've got 4 parts to the session today. First 2 are very similar in terms of what they cover, but looking at PDisp and XDisp. Firstly, Shiva is going to show you more about PDisp, so what it does, and an example of building a model, bit of an overview there. And then Vikram will cover XDisp, same sort of thing. And then we're going to have a short break, and then after that, we will Raoul will show you how they can be used together. So the outputs of PDisp can become the inputs of XDisp, and also show you some techniques for automating with these products, so via the common interface and using JSON file formats. So that's broadly what we'll cover. And I think without further ado, I shall pass over to Shiva to talk about PDisp.
Thanks, Mark. Hello all, my name is Shiva and I'm part of the Oasis geotechnical software team. So PDisp is one of our popular soil movement software products. So in this section, would be briefly discussing about the kind of settlements that PDisp can calculate, the methods that we use to calculate those settlements. I'll show you how to set up a simple model and do the elastic analysis, and we'll also see how those results can be viewed in the graphics form and also in the tabular output. So then we'll see a simple case study, how PDisp is used in comparison with complex FE model. And we'll also be providing you additional reading material which would help you in like knowing the software better and the input and output parts of the software. So PDisp, what it does. So PDisp stands for pressure induced displacement. So it basically calculates displacements, vertical and horizontal, due to the application of pressure that could be loading or unloading. So and some of the typical uses, as mentioned earlier, we can calculate the ground settlement due to loading, flexible footing, and we can just inspect how the tunnel line would settle because of any construction activity or some excavation that is happening. You can also kind of get the general sense of how the vicinity would behave due to loading and unloading of the soil. So the material model in PDisp, it's completely linear elastic. So no failure criteria like the Moore-Coulomb one are considered here. It's purely linear elastic, and the material properties are described by the Young's modulus and the Poisson's ratio. So assumptions and limitations. So for Bosnick stress calculation, we have to define the Poisson's ratio, the global Poisson's ratio that is used. And Bosnick's method is sensitive to the number of intermediate displacement points that the user specifies in the stratum. So sublayers are nothing but the user has to specify number of intermediate displacement points in each stratum. So then the program divides that stratum into different sublayers. That's what it is all about. And it also depends on what E ratio that you have selected. If the E ratio that you have given, if the model is of like a different E at the top and bottom. And the limitation, there's no lateral fixed boundary here in this case. PDisp, there is only like the vertical boundary. You have to specify the rigid boundary level. So coming to PDisp solver, so there are basically like two solvers that PDisp provides. One is the elastic one and the other one is the consolidation one. So the elastic gives you the immediate settlement, also called as the instantaneous settlement. The consolidation solver would give you the consolidation or primary consolidation values and the secondary settlement creep. So coming to the elastic solver, so PDisp provides you two options. One is the Buzynsk approach and the other one is Minlin approach. So this table that you see here illustrates what Minlin analysis and Buzynsk analysis can do in this software. So as you can see, Buzynsk is purely vertical. You get the vertical settlement and the vertical stresses. Minlin, however, doesn't do stress calculation, but it can give you horizontal displacements provided that option is checked in the analysis options pane. So there is separate option for that. You need to check that to get the horizontal displacements. And additionally, in Buzynsk, you can have the soil nonlinearity as well. So there are nonlinear curves where you define the degradation curve that are used to calculate vertical strains at various points. Consolidation, as we know, consolidation is just like what would happen. Consolidation is something that would happen with the expulsion of water over time. So this would vary from soil to soil. And PDisp, as I told you, would give you primary consolidation and secondary settlement. So primary consolidation is due to the reduction of volume due to the reduction in dissipation of pore water pressure. Secondary settlement is assumed to start at the end of primary consolidation. So in PDisp, it is assumed that it starts at 95% of consolidation. So the reduction in volume in this case is purely due to the rearrangement of the soil particles. So the pore water pressure is constant. So in calculating primary consolidation, total primary consolidation, you have two approaches in PDisp. One is the MV and the other one is the CC approach. So this MV approach is completely linear and CC on the other hand is the nonlinear approach. So what would the consolidation solver do in PDisp? So in the consolidation solver, first it calculates the excess pore water pressures at various points in the model at various calculation points. And then these excess pore water pressures are used to calculate the degrees of consolidation at various time steps. So you integrate the initial pore water pressure and the excess pore water pressures at the corresponding time step, and then you do the degree of consolidation calculation. So once that is obtained, you do the like settlement time, what primary consolidation happens at every time step, so that you can calculate. So basically you see the basic differential equation there. You need to solve that to get the excess pore water pressures at various points. So PDisp uses a numerical approach, finite difference method. So there's a specific method called as Crank-Nicholson method. So in this method, this method is explicit in time, and this equation is solved to get a solution, and this solution is applied at various points in the grid. So the grid that you see on the right hand side corresponds to each point on the grid corresponds to the excess pore water pressure at a particular time step and at a particular depth. So this would generate a system of linear equations, and this is solved using the matrix approach to get the excess pore water pressure. So for this, we need boundary conditions. So we have the top and bottom boundary conditions, and we need to have this initial condition values as well. So as we know, at time step 0, the stress increase is completely taken by the pore water pressure and nothing by the soil skeleton. So what PDisp does is, irrespective of the elastic approach selected or not, behind the scenes it does Buzynski analysis, because Buzynski analysis gives you stresses. So the stress increments are calculated and they're substituted here for the time step 0 as excess pore water pressure. So that would help you in solving that system of linear equations, and you would get the excess pore water pressures at various points. Once that is done, PDisp reports 3 different types of settlements, both in tabular form and in the graphical form. So that those are like immediate settlement through elastic approach, and then you have the primary consolidation and secondary settlement through consolidation solver. So this is a sample graph generated in PDisp that gives you like different kinds of settlements at a point. So you can see as you move from left to right for different time steps, what's the displacement that you get for a point. So all different kinds of settlements are displayed there: immediate, primary consolidation, and creep. So even the total sum of all 3 is displayed. So how to build a model? So what you need for inputs? First, what we need is displacement entities. So these entities could be points, lines, polylines, which are like a series of lines, or grids, which would cover like a wider area. You can have the contours seen using grids. So those are the displacement entities that you can input, and those are needed. So, and we need the loads that induce this displacement. So there are like 3 different kinds that PDisp allows. You have the rectangular loads, circular loads, and the polygonal loads. Rectangular loads and circular loads, you can define them in both the planes, horizontal and vertical planes, and you can define them as normal loads and also as tangential loads X and Y. However, polygonal loads, there is a limitation. You can define them only in horizontal plane and only in normal direction. So you don't have the tangential loads in this case. Polygonal loads, internally the solver converts them into rectangular loads. So that's how it would calculate. And for that, the user can input the number of rectangles those polygons can be split into. So the more the number of rectangles, the better the accuracy. So that's about loads. And once these are defined, you need the boundary, the rigid boundary, vertical boundary. So at this point, the vertical settlement would be 0. So that you need to define, and then you need to select the kind of analysis that you want to conduct. Is it the elastic or consolidation? And if it is elastic, what kind of method? Business or milling, and if it is consolidation, for each atom, what kind of approach, MV or CC. And then you need to model the ground. So this is modeled with a combination of profiles and zones. So soil profile is nothing but a series of strata. So you can define the material properties from top to bottom, how they would vary. So each stratum would have different properties. And then soil zone is basically like the length and breadth of that model. So there is a sample example here. So there is a sample model here. So you have 2 zones here in a single model. So zone 1 is associated with soil profile 1, and zone 2 is associated with soil profile 2. So both are like 100 by 100 blocks. And in the soil profile 1, you can see there are 3 different strata with different properties. And in soil zone 2, you have like 2 different strata. So this is how the zones, this is like illustration of zones. So you would be just inputting the length and breadth of the model using the soil zones in the table. And we'll now see a simple model. I'll show you how to set up a simple model in PDisp. So what we'll be trying to do is something like this. So this is the model that we are trying to set up. So you have a soil block. You have three different kinds of rectangular loads. So the green strip that you see is an embankment, and you have the flanks. The blue ones are the flanks, and there is a circular water tank close by, and there are four grids defined. So in the vertical plane and in the horizontal plane to each, and there are few lines defined underneath those loads. Those refer to the tunnel alignment. So this is what we'll try to model. So I already have an Excel sheet. So this would have all the information. So I'll just try to model this from scratch. So if we set up a new model, first we'll add the soil profile information. So in all geo software products, you can just copy paste from Excel. So this is helpful to engineers. So this would have saved their time. So if there is a model, if there is a table defined already in the Excel sheet, I'll copy this and then just say paste. Control V or right click paste, both would work. So that's the soil profile defined. And now I would define the soil zone profile. So, and one useful tip in this software is like you can split the view. So this is a tab view. So if you want to see them side by side, I'm just pressing Control and dragging this using the left click. So that would split the view. So it would be useful for you to just see both the tables. So I'm copy pasting this. So that's the soil zone defined. We'll close this, both of them. And now we have the rectangular loads. As said earlier, we have the embankment core and both the flanks. So no tangential loads here. In this case, only normal loads in horizontal plane. So with rectangular loads, copy pasting this to OK. And then we have the circular load from the water tank. So we'll copy this as well. Editing this. Circular load done. Here again, no tangential loads, only normal loads. And now we define the displacement entity. So in this case, there is a point and we have lines at tunnel crown level and, perpendicular to the tunnel, and then you have the embankment level, and similarly grids to get to view the contours. So we'll copy the points first. Close. Just okay, so that's a displacement point. We'll copy the lines now. So in the program, you can just activate them or deactivate them. So if you say no here, then that would save your time. Those lines wouldn't be calculated. Lines or points or grids, anything. So now to grids. Okay, we copy pasted the grid. So everything is done. We can view that model in the 3D graphics. So this is how the model would look after all those additions. If you want to just deactivate parts of visualization, you can do that using the graphics ribbon. So you have the graphics ribbon here. Now you can view all the items as you can see here. But if I want to just deactivate the grids, I can do that here. So you have the lines alone here. So that's the tunnel level, and that's at the ground level. And you can also do those things using the settings wizard. So if you go to settings wizard, you just say grids and apply. So those are the grids, so and various points on the grid. Coming to the view, you have the plan view in 2D plan view in PDisp. So this is how the plan view would look with all that model intact, and you also have the cross section view that would give you the cross section. So this is how the cross section would look. And to save some time, I've already analyzed this model, so I'll now show you how those results would look. So this is the analyzed model. You can see the contours here on those grids. So stress contours. So I can, since this is Buzynsk analysis, we only have elastic settlement. So if you can show here, this is just Buzynsk analysis, and we're calculating displacements at load centers as well. So, and this should, in this horizontal boundary level in this model is -51, ignore this one. So that's -51. So this is how the final model would look. So these are the contours, and you can view the deflected shape as well. So if I want to view the deflected shape, this is how it would look. And if I want to view lines deflection, that I can do, I'll deactivate the grids for time being. So that's how the tunnel line would displace. So this is about the example sample model that we wanted to explain. So back to the presentation. So yes, so this is about setting up a model and analyzing and viewing results. So I'll also show you the results. So there are various graphs that you can see. So the graphs are available only for displacement lines. So you can see the time dependent graphs. These are for consolidation problems, but since this is like an elastic analysis, we have not selected consolidation in analysis options. So we don't have that, but coming to the elastic on settlement. So you can see this is the vertical settlement. Since this is Buzynsk, we have only the vertical settlement, and you can switch between various lines using the drop down there. So this is how those lines would look after settling. And you have the stress graphs as well. You can switch between various those lines, and you have the strain graphs, various lines. And additionally, we have something called a soil column displacement. So if you activate this, you can at a point, in this case, just some random point 0, you can view the displacement versus level as you go from top to bottom, how the displacement will vary at that point. So that you can view, and you can modify the point values and types, view the types of settlements as well. So that's to do with the results and graphs. And a case study. So this is like a case study. You have a building, a series of buildings there. You have the metro station there, and you have few tunnels. So this particular thing is modeled in PDisp, and that's how those tunnel lines would, that's how the profile would be, displacement profile would be of those tunnels and the grids that are specified at the ground level. And this is remodeled in a complex FE software, and that's how the results stand against each other, the PDisp results and the FE software results. So this is about the case study. And coming to the references, so there are certain webinars that are already conducted on PDisp. So you can click those links and go to those webinars, and that would give you a better understanding of what all things PDisp can do. And there are also short tutorial videos on YouTube, so that would help you understand the various features of PDisp, how to input them and how to view results. And additionally, at any point, if you want to view the help manual, so there is a shortcut. So suppose I want to view help regarding soil profile information, I can just say F1 and I pressed F1, and that would take me to the corresponding section in the help manual. So you can view the related information there that would help you with the working with PDisp. So this is all about PDisp. Thank you, and over to Vikram. Vikram, I'm stopping sharing my screen. I'll stop sharing my screen. You can carry on.
Thank you, Shiva. Are you able to see my screen?
Yep.
Yep.
Okay, thank you. Hello, everyone. Good afternoon. I'm going to give you a brief presentation about XDisp, continuing from where Shiva left. So XDisp, as the name suggests, is excavation-induced displacement as opposed to PDisp, which is pressure-induced displacement. And in this presentation, I'll briefly give some introduction about the tunneling, mining and excavations, and sage construction, how they induce the ground movements in the vicinity around them, and how XDisp can be used to predict the ground movements due to such tunneling and mining operations, and also how XDisp can be used to estimate the damage that can occur due to either due to the ground movements on either the buildings or even the utilities such as the sewers, pipelines, telecommunication cable lines, etc., which are in the vicinity of the tunneling or mining related operations. So after that, I'll quickly show how to set up a small model in XDisp, how to analyze it, view the results, and interpret them. And following that, I'll quickly show a very brief case study on how XDisp is used in the typical urban metro construction environment. Finally, I'll close my part with giving some references on this presentation, where you can also refer some previous webinars, etc. And again, as mentioned earlier, XDisp is mainly used to calculate the ground movement to excavations, and it's typically used for modeling ground movement due to tunneling excavations in soft ground, and also shaft and retaining cuts and mined excavations, etc. Then what we have in this slide is the ground movement profile that that is typically observed due to the excavation of tunnel underneath. Actually, there are I mean two different profiles across two different cross sections. If we take the cross section transfer to the axis of the tunnel, we get the transfer settlement trough that is shown in the bottom left corner of the slide. And if we take a cross section along the axis of the tunnel, parallel to the axis of the tunnel, we get a longitudinal settlement trough, which is shown on the bottom right corner of the slide. As can be seen, both these tend to resemble the inverted Gaussian normal distribution curves. So what happens is internally, XDisp uses certain closed form three-dimensional ground movement equations based on Atwell and Woodman and Harrison, Alvarado, etc., which allow you to predict ground movement occurring at any point in the vicinity of the tunnel of a specific geometry and a specific embedment depth, etc. So one thing to note is this particular relationship, or rather these equations, are mainly empirically based, and they are not analytical based. That is, they don't use stuff like Young's modulus or Poisson's ratio, cohesion, etc. So unlike PDisp. And instead of that, the key parameters that the user is expected to enter are the volume loss incurred due to the tunneling operation, and the trough width parameter, which controls the sharpness of the ground settlement trough. So the thing is, for volume loss, there are quite a few. I mean, quite a few parameters which affect the estimation of volume loss. So things like the type of tunneling method, such as TBM or sprayed concrete lining, etc., the type of soil, the groundwater conditions, the flexibility of lining, the speed at which the construction take place. All these parameters tend to affect. So it is actually many others have provided some guidance on this, on how to calculate the volume loss based on past case studies, and also some empirical approaches are also available in literature, which considers the geometry of the tunnel, the depth of the clay cover, tunnel diameter, etc. So the user is, I think, the user is expected to come up with this volume loss parameter beforehand by taking these things into consideration. And then once this volume loss is estimated, for example, this shows a typical volume loss data that is for tunneling in London clay or Lambeth group for different type of tunneling operations, like using TBM or net pressure balance method or sprayed concrete lining, etc. But this is just a very generalized guidance, and it's very much specific to what the user has in actual site. So once the volume loss is entered, the second important parameter is the trough width parameter, which is K. So before K, there is this parameter I that is very heavily used in the three-dimensional equations by Atwell Woodman and Harris Alvarado. So that is simply the distance of the inflection point of the ground settlement trough from the axis of the tunnel. So this tends to like one of the simplest equations assume it to be linearly proportional to the depth of the tunnel center line under the ground. So, but see, this is a snapshot from the help manual, but like there are many other different methods available, like Mayer et al, etc., ribbon sync method, New O'Reilly, etc. So, so using those empirical methods or some general guidance, the user needs to enter this trough width parameter K to control the shape of the ground settlement profile. So once these two are entered, the basic, the basic tunnel dimensions, the depth, etc., need to be entered, and with those, the rough approximate ground settlement profile is computed by the program at the desired calculation points, which may be in the form of grids, lines, or points, whatever. So this shows the variation in ground settlement profile between the clay type of soil and sandy soil. It can be seen that the clay soil typically has a higher K value, and that typically leads to much flatter ground settlement profiles compared to the sands, which have much more sharper ground settlement trough. And once the settlement of the ground due to tunnels are found, similarly, if there are other elements which cause ground movement, such as mines or even embedded wall excavations, those can be entered. Actually, the embedded wall excavations feature is mainly based on pre-entered ground movement curves for vertical ground movement and horizontal ground movement behind an excavated retaining wall. So what the program does is it will try to superpose various ground movement curves at different points in the ground and come up with an overall settlement. So primarily at the heart of the solver, we have direct linear superposition of displacement fields that come from various sources, such as either tunnels or maybe embedded wall excavations, etc. And they are added up. And once these displacement fields are added up, we then go to the next stage of trying to evaluate the building damage or even damage to utilities, etc. So regarding one other interesting thing in XDisp is it will allow you to model a stage construction process. So for example, in this particular slide, I am having about 4 different buildings. So each of them, like underneath them, we have a construction of tunnel taking place with some embedded wall excavation and shaft, etc. So one thing that you can see here quickly is that At different stages, different advanced lengths of the tunnel are modeled and different depths of the excavation are modeled. And for each stage, you can see that there is the color of those building changes. The color is an index to the damage category. So if it is green, there is very less damage, which is category 0. And towards the red, you have severe damage. You can see that as the tunnel advances, the second building from the left suffers the most serious damage. So that is how this can be used. And again, one of the important things here is defining the damage. So the solver in PDisp, solver in XDisp uses the theory on the damage by Berland et al. 95 paper. So there are various categories of damage ranging from negligible to very severe, and there are some typical descriptions and approximate crack widths and limiting tensile strengths, etc., which are taken into account by the software. I think the software internally mainly bases its damage category based on the limiting tensile strength that can occur. So once the ground movement profile of arising from all the excavation tunnels, etc., is found, the variation of the settlement across a particular utility or a building facade, etc., is found, and appropriate damage category is assigned by the program. So typically, like one of the values of XDisp is like when you are dealing with a large city, maybe, and if you are undertaking some construction of underground metro, etc., there are too many buildings that can be impacted. So I think one of the approaches is to first identify which buildings are more vulnerable and which are less vulnerable. And as a first step, I think, which is stage one can evaluate the settlement contours that can be generated in the ground in the desired area of interest, and then there itself we can try to filter some of the structures which have very less potential of the damage. Then we can move over to the second stage assessment, and finally to the detailed evaluation. So in the next slide, this will be more clear. Like in the stage 1, once we have, this is a typical basement excavation, and which is also interfacing with the tunnel construction. So basing on the settlement contours, which are shown in the figure on the right side of the slide, we can find the critical areas, and try to screen out the buildings which are imposed to ground movements which slope which is greater than, I mean, which is much lesser than 1:500, or settlement which is less than 10 mm. Then you can consider other buildings which are subjected to some potentially damaging ground movements, and only those buildings will try to do the damage assessment, which is based in the solver in XDisp based on Berland theory. So the whole building is modeled as a kind of deep beam, and both bending and shear modes of deformation are taken into consideration to evaluate the critical tensile strength that can occur in both the cases. So once this is done, we actually try to come up with the damage category. Again, if we are talking about a long building, there may be certain portions of the building which are hogging in nature, some are sagging in nature. So the program automatically divides the whole building facade line into such zones, and tries to come up with relevant damage categories for those individual segments as well. So this is the second stage, and in the second stage, if it is found that there is some serious damage that is occurring, at that point, I think people can use more advanced tools and finite element software to take into account the explicit material properties of the soil and the structure, and come up with more accurate predictions of the damage. So that is about the damage assessment. And for the building, similarly, the same thing can be applied for utilities as well, which are like sewer pipelines, gas pipelines, and even communication cable pipelines, etc. So in these cases, I think there are two broad categories. One, some things are related to like jointed pipelines, others are continuous pipelines. So based on the type of the pipes or utilities, I think different damage mechanisms are there, and the program takes into account all of these based on what the user has specified, and it tries to check if a particular utility, which is typically modeled as a line, fails due to maybe maximum tensile strain or too much pullout or maybe joint rotation and stuff like that. So that is how I think the utility damage assessment is done, and the user can quickly see in a particular area of interest. There are many utilities. There is this coloring scheme like the one that I showed you earlier for buildings. So only the utilities that are failing, they are marked in red, and that makes it easy for the user of the program to identify the vulnerable elements and then work on some countermeasures and retrofits, etc. So and this is about the damage assessment for utilities. And similarly, there is also one rail damage, but I am ignoring it for the present. But it's always available in the help manual in more detail, wherein things like the cant and twist, all those things also are calculated by the program, and it is checked whether the rail are going beyond the tolerable limits, the cant and twists and stuff like that. So basing on that also, the program can give you what type of damage is expected in various rail infrastructure. And now coming to the next part of the presentation, I'll quickly try to take you through setting up a model in XDisp. So what generally what we have is like you have to first select either the tunnel type or mine problem type. We cannot have tunnel and mine existing together in XDisp. You can select either one of them. Then for tunnels, you can also select the embedded wall excavations in conjunction with them. And once you define these geometric elements, such as the tunnels, mines, or embedded wall excavations, you then focus on specifying the required points at which the settlements and ground movements, etc., need to be calculated. They can be either lines, grids, or points, the same way that is there in PDisp. And then think any embedded walls and even buildings, utilities, all those things can be defined. And once that is defined, you can perform the analysis, and then you can get the settlement contours of the required area of interest, and then perform the damage assessment, trying to find the damage category, etc., for building utilities and rail, etc. So once that is done, okay, I'll briefly set up the model. What I'll do is, I think the same way that my colleague Shiva has shown, I'm having this Excel spreadsheet which contains the required information for setting up a model. So if you can recollect, Shiva's model had some embankment and there was some circular water tank as well. I think this is pretty much similar to that. The only difference is here we are also drawing some utilities and also a structure which is represented by the four facades on north, east, west, and south. So the other thing is these utilities are running under the embankment, directly under the embankment, these three utilities. And in addition to that, a tunnel is expected to be excavated at right angles to the embankment under it, and it passes under the building. So the main objective of this exercise is to try to find out whether there is any scope of damage to those building facades. So that is the main objective. So we start off with, I think, displacement lines, points, all those things are pretty much similar. So I try to go through them fast. But the difference is probably in tunnel geometry, etc. So what I'll do is I'll quickly try to set up a new model from scratch and guide you through it. So as soon as we open a new file, we need to specify the type of problem that is in the specification. We go for tunneling, we apply, and then after that we can specify the tunnel directly. the tunnel diameter, the starting point, ending point, and what is the ground loss parameter, and how do you want to derive the K and stuff like that. So these data are already available for me right now using this Excel spreadsheet. So once I have this, I'll just paste it in here. And then I'll go back into the displacement data and start filling them up one by one, which is right here. I think some of the critical points of interest are the center of the model and the tunnel ground center as well, which is under the ground. So then we have lines which represent the utilities, which I explained before, which lie underneath the embankment. So these are represented as lines. And one quick thing regarding this. So L1, L2, L3, they are the utility line directly under the embankment. So, and tunnel center line obviously traces the axis of the tunnel, but at the okay, it's at the axis of the tunnel. Apart from that, we have the power station facades on the north face, south face, east face, and west face. The starting and ending points are done. And one thing to note here is actually some of the calculation methods make a differentiation between how the ground movement profile is calculated at the ground surface level and also at the subsurface level. So the first 4 points, first 4 lines are underneath the ground surface. So appropriate surface type for tunnels has been selected. And for these things which are above the ground, the power station facades, they are using the surface type for tunnel movement calculations. So once the tunnel and the grids etc. are defined, we can move ahead to the specifying the buildings and stuff like that. So this is a building damage assessment. There are some standard damage categories, Berlin damage range limits. But if you are interested, you can define your own damage limit. And here we need to specify the building geometry and its properties, height, etc. So these things again, I'm just copying from the Excel sheet. So we have these, and I'm saving the file. So once this is done, we have acceptance. We need to define the cross-section dimensions of the utilities as well. So we get, same thing, the internal diameter and the wall thickness. So we fill in these things as well. And acceptance criteria, we can use some defaults. We can use the tab key, which is a shortcut, which will just copy in the default values from the defaults column above. So I'm just tabbing through all these cells. And once that's done, I move over to defining the specific utilities, which are the communication cables. And these are copied over from here. And once that's done, we can pretty much go ahead and try to perform the analysis. So once the analysis is done, you can view the results. So what we have is the 3D graphic view as well. You can try to look at the Output Explorer and try to get the 3D graphics view. And I think this is pretty similar to what was shown in PDisp. I won't go very much into detail here, but what you can see here is like you can go to this graphic settings widget as well and try to see the various results such as displacement and jet direction and contours and stuff like that. And the other thing is you can also look at the damage for buildings. So these are the typical interaction charts that are generated. So there are various categories. This is for power station north phase. So it will these are this colored line are the categories: green for minimum negligible and red for the maximum, category 3 to 4. And the black line is the actual situation of the building. So it lies between category 0 and 1, so it is safe. So that sort of a quick evaluation you can make. So then for utilities also, there are many such things such as the displacement profile along the utility and the rotations, pullouts, axial strains, etc. So the users can quickly go through them and try to see if there is any vulnerable utility or building facade that need to be examined in more detail. So that's about how to set up a model and stuff like that and view the results. So next, I'd quickly go through the other parts of the presentation. I think we are running short of time. So this is a typical case study again, and so this is actually from the construction of an underground metro in one of the urban areas, and it has an incidence of high groundwater level, and there are many wooden piles, etc. So it was critical to find the impact of doing construction of underground metro such as excavations and tunneling operations. So for this it was used as well, and we had you can see the typical ground surface that is scaled, magnified a lot, but essentially that shows the contour of the ground due to that underground metro construction. And those blue colored things are the facades of the various buildings. So the buildings damage categories were examined, and even for utilities, I think the type of the horizontal and vertical displacements were evaluated to check for any possible damage. So that was what was done. I think you get a large number of charts when you are dealing with multiple buildings and stuff like that. So next is you have that feature of even doing bulk chart export and stuff like that. So those are also some things that are handy for the user. And more thing can be found in the help manual. Since the time is short, I have only covered tunnels in a bit more detail than embedded wall excavations, etc. But you can always refer the help manual. And also there are some 2 detailed webinars that the links are given here in this presentation. You can refer them later. And we also post some tutorial videos on YouTube regularly, so they can be handy as well. So that concludes my part of the presentation. And before that, I think it's worth having a look at this slide, especially when users are entering data in the tables. Like other than copying pasting, I think there are many trips like typing equal to and double equal to or tabs to enter data quickly in the table. So you can refer them at leisure when required. So that is my part of the presentation, and I think it's time for a little break. So over to you, Mark.
Thanks, Vikram and Shiva. Fantastic. It's very informative. So I think we're going to switch over to Raul's screen now. He's got the slides at the same point. Just have a short break if anyone wants to grab a glass of water, and then Raul is going to introduce himself and then talk about firstly using PDisp and XDisp together, linking them. So yeah, just bear with us a minute or so. I'm back shortly.
Thanks, Mark. Hi everyone. So this is Raul. I've joined Oasis and Arab earlier this year, and I am the assistant product manager for the Oasis Geo Suite. And yes, I've got a background in as a geotechnical engineer, project delivery and everything for about 7 years, and but I've always had, I mean, not that long, but the appetite for automation and making life simpler for us engineers on in terms of automation, finding ways of speeding up routine processes, and and numerical modeling as well. So the bit I'm going to be showing at the moment is how we use together the output of PDisp and XDisp. And in the process can be used both ways, in the sense that we can use the outputs from PDisp into XDisp and then from XDisp into PDisp. It makes more sense though to get in terms of the building damage assessment and utilities, because once you bring the field into XDisp, then you can do the damage assessment. If you're not interested in doing that part of the exercise, then getting the field disp, the field displacement, the displacements from XDisp into PDisp, it does work too. So basically, which very quick summary of what Shiva and Vikram have presented already is that we can unite the pressure displacement calculations from PDisp into XDisp, and that's the result of both. It's a summation. It's an addition of the displacement fields of the two tools. And a quick summary of what I'm just going to show is just getting those two together. And without further ado, I'm just going to show you how we can do that. So I'll just open the right file. So this is the generated PDisp model that you've been shown earlier. And basically what we are going to do is just here in the graphics part of the ribbon, you can have different ways of viewing the results. One I particularly like looking, you can also look from the top. So just to make sure that you've had all your inputs correctly and you're happy with your outputs. But then looking from the side is just getting that better view of the bulb of stresses and the displacements, depending on the method you've chosen. And in this case, we are just going to bring in the PDisp results. Sorry, the XDisp results. So we just go up here on the file button on the icon. Then we can import either the JSON file, which I'll cover that later, or the native file format from XDisp. We chose the latter. And I need to select the file, and then it's warning me that it's going to invalidate the current results, which I'm absolutely fine with that. And I'm just going to say OK. And this gives us the chance also to import those grids, those lines, points that where we've obtained the results. And I'm going to switch that off because we've got coincident grids and features that contain those displacements. And I'm just going to be importing the purely displacement results at the right locations because they are coincident. And again, nicely, I'm just making sure that this is happening, and this is the amount of results we got from the XDisp assessment. And yeah, I want to continue. I just click on yes. And now we need to just reanalyze, and that operation does the calculation about the pressure, that embankment pressure we've got, also the water tank that we've produced for this synthetic analysis, and then we just click on analyze again. Just takes a few moments. We can here see that the model has run also both for Bosinesk and Mindlin, and it's showing us the difference between the two methods in case we can spot major discrepancies in which we just need to make sure that we are inputting the data correctly. and according to the model. So as we can see now, we are also getting this effect of the tunnel excavation from XDisp, and I'm just going to show quickly how this looks on the side. We might want to change as well just the graphic view one shown before from the setting wizard, which is quite useful. And we can just maybe reset in this case by clicking in editing the contour values. We just see that it's slightly bigger the displacement, and we just click again and just give a sensible range of values, so we can then just plot that accordingly. A minimum of, say, 10 mil, and then we get a maximum of 140. By applying this, it just shows again that model. And then we could just save it and then have that model up and running. So I'm going to do, and then we can do exactly the same exercise the other way around. So we can bring into XDisp. I'm just showing that same model that Vikram ran earlier, and we can explore from the sides where we can see only the influence of that tunnel alignment below the building and the utilities. And then what I'm going to do is just exactly the same operation. I go into import, and I'm just going to click in the native file support on PDisp. I'm going to select that model that we have run already, and then we import again, we are only interested right now on the results because we've got coincident grids and lines and points in terms of the results. So we just want to bring those in. Again, we have a similar amount of results because we didn't have the utilities and everything in PDisp, and those are excluded in this case. And again, we are warned that it's invalidating our results, and this we can see then the naked geometry of that we have the input, which is the 3 utilities across. Then we've got the building and the tunnel below. Then we just reanalyze the model, and the combination of the displacement fields has occurred. I'm just going to show it from the side. You can see it's been broken temporarily, the display of the colors, but that's due to the scale and the magnitude of the displacements. So we just quickly go back to the settings wizard, and here in the displacement locations, again, we just reset the contour values. We bring them back to a sensible range, which takes just a few seconds. Just bring it back. There we go. We recover that displacement field from PDisp, having also the combined effect of the tunnel excavation below. And then, as we can see, I don't know if you've noticed, but these 2 facades that originally had they were not affected at all by the nearby, because the embankment pressures were not modeled in XDisp, and now we've seen that those have moved on to category 1, which is very slight damage. And this is the way we combine the results of the both, and then we can further expand on the knowledge and the assessment of our models. Also in the graphics, just as a matter, we can change to perspective. Some might prefer this view, and there's a lot to play around, which I'm not going to go further at the moment. And I'm just going to close this bit and go back to the presentation. So bear with me. Right. So about linking the two, it's a matter of going back to the help manuals if you've got any doubts when constructing your PDisp and XDisp models. And as a matter of fact, we also have a webinar a past webinar in which we explain maybe a bit more detail how we can combine the results of both to predict building and utility damage due to ground movements. And then that moves us on to the last part of this presentation, which is the COM interface and a bit on automation and workflows. And I guess first of all, just to remark that the COM interface it's a feature that it's present across the whole Geo suite of products, and it's available there. And there's a section in our manuals where you can learn more about it and which functions have been made available for you to interact with. But let's go back to what is COM, what stands for, what we can do with it. So it stands for Component Object Model, and it was thanks to Microsoft. It was developed in the early 1990s, and it's a way where we can basically communicate with a particular software bypassing using the graphical user interface. So it's a one-to-one conversation we can have, and then ask the software to run some features or some parts of a model that we're interested into. And why would you be using that? So there's primarily is to automate and to get those more probably tedious tasks that wouldn't happen if you just had a model to analyze, but that's not the case these days where computer power has increased and we are able to create and analyze plenty of models, sometimes in the order of dozens, if not hundreds, and then to get those more tedious and repetitive processes at bay by using this tool, and also in the context of optimization and sensitivity analysis. Again, when you have to run multiple models to understand the variability of your ground parameters or anything of interest on your models, and then to embed as part of bigger workflows in the organization or on a particular task. The COM interface, though, is slightly less flexible than the JSON file format currently, because the attributes and functions that have been exposed from the core of the code have been made available more as a matter of requests from clients, both internally and externally to Oasys and ARAP. And then as a very quick comparison, basically is this TV analogy, hopefully it makes sense, is before with the old tellies, you would have to go there in person, like go across the hall or something, and then the living room, and then go touch the buttons and adjust things, and then maybe probably kick until you get the right frequency or the right channel until it works. While now we've got smarter televisions in which we can do things remotely. You don't need even to go away from the comfort of your sofa if you're sitting, and then you can even control it from your mobile phone if you've got that availability. And then yes, that brings us into what's the other part of things, which is what's JSON. So JSON stands for JavaScript Object Notation, in short, and it's an open standard file and data interchange format, which basically makes our life easier to share model results or files even with clients, but also in between teams. Say we are running some models with the geotech team, and we need to convey some of the results into structural teams. So that's that can embed that information in wider workflows. And why would you be using it? I just covered that really, but it's a way of letting that information flow easier in between teams, and also outside your organization if that's the case. And this little is an extract from of the file that we've been using today in the webinar. It just nested structure, so you get the declaration of the different variables and different parameters, so then you can access that from outside if you create some scripts to do so. And now I'm just going to go quickly. So I'm just going to show from PDisp manual the documentation, what that section and what embeds, and then I'll go through some examples that we've prepared for today's webinar, in which we are going to see how we can interact with a file. For example, in this case, duplicating it and creating under a different name, so we can avoid some of those little disasters that can happen when overwriting files, and that's we can have it as a sandbox and play with that file without altering the original one. Another example where we can vary parameters, in this case the shape of one of the loading patterns that we've included, and also something a bit more to do with the ground as well, which is we could be interested in stiffness of parameters. And in the final example, we are going to get, after we've been building up on what we've been showing, then just an iterative process where we can display and plot those results as the model is calculating, so we can have a better understanding of what's going on with our model. So I'm just going to quickly shift to the PDisp manual of the current version. So on section 4 is the program interface, and where we have the development team have put together the list of the currently declared functions. So if for some reason there is something that it's not in there, then it's just a matter of just please get in touch with us, and we will make our best to satisfy if possible on that. And then yeah, there's also some VBA examples, so Visual Basic language, and also C++, so you can get more knowledge from there. And back to the presentation. So I'm just going to show how we can duplicate files in this instance. So I'm just going to go to an Excel file that we've prepared for today, and just bear with me. So we've got an Excel sheet here in which there are a few cells that are quite important, and they have been renamed. Just before we go into that, to activate your Visual Basic tab, or is actually the developer tab in Excel, you need to go to the options in here and then get it activated. You may need help from your IT or from your colleagues. I'm sure you might already have that because you need it for creating macros and other sorts of automation tools in your work. And then once you've got that, we've created some cells which are deemed to have the paths for our input and output files. We have created a few buttons which are going to be running the examples I'm just going to be showing now. And then also I'll just show briefly the Visual Basic script that has been created on the back of it. So just move to the first example. So in here we are going to duplicate an existing file. So you start the declaring on the example the name of that example, which is and it starts this subroutine. Then you've got the chance to create with that starting symbol. Then you can comment. So the green lines help whoever is going to be the receiver of that code to be able to understand better what has been done on the back of it. And what we do basically with the following lines of code is we open an existing file. We call the application, the executable. So we open PDisp effectively. We ask to open PDisp, and then what we do is we call to go to the path that we have selected in our Excel file, where it's declared which file we are interested in copying. Then also the next line, it checks that the data that we have, that it's inside that file is correct and it's ready for analysis. And that's what the next block is doing. And what it does then, once it's happy with it, it runs it, and then we can save it in our output file cell with a different name. And then once, just for the sake of it, you also want to close the application, and it just saves the results afterwards. So before we go to example 2, I'm just going to be running that very quickly on screen for you. So just to show you, I've got it's saving the sample result in my temporary file in my C drive. So when I run the example, it just takes only a few seconds, and it just goes back to it. And you see it's just being created there. There's the timestamp. We just double click on it, and we just basically got our previous model that we've run earlier but under a new name, and then we can start modifying and interacting with it from within or from without the COM interface. Slightly more, adding a bit more of complexity to this. Say that we want to assess the impact of a change in the design. For example, we know that sometimes late in after we've run all the models and everything, oh, by the way, please, can you change the shape? The tank is not going to be any more circular. Although that probably is not true, but we can accept that for this example and say, well, it's going to be a square because now it's a warehouse instead of the tank. We've changed the shape, and then what we want to do in this case is we are going to open and check the existing PDisp file. We are going to be deleting that load that we have imposed earlier, and then we are going to replace it with a rectangular load, reanalyze the model, and then we go back to the results. So the way this goes is that we use the same part of the structure of the subroutine, in which we are going to call the application. It's going to open PDisp, and we select the cell to the path of the file that already exists. We are going to go in and actually say, please, can we delete? We are going to check how many circular loads exist, and it gives that's the dimension, and it's an integer, so no half shapes there. It's 1, 2, 3, n, however we need, and then as long as there are more than one, then we are deleting the last one. So that's what we are asking for it in that if little loop in there. So next thing we do is once we've deleted that circular load, we say, all right, so it has changed. So we are going to include a rectangular load as part of our design. And what we do is we need to include in here all the fields that you would have to implement manually within the PDisp as well. So by getting a declaration of those, and for that, I'm just going to jump quickly to the manual, I think. So is how much of those it's shown. It's in the example. There's a few of those ones in here, and it's here is the enumeration. So for rectangular loads, apologies for that. I'll just make it bigger if I can. Scrolling. There we go. So it's the enumerations and structures. So here for rectangular loads, that's all the parameters I need. So I get that from the manual, and I can just tidy up then myself. And then we, in this case, we are using a similar area, loaded area from the original circle, and we use exactly the same load. So it's 150 kPa. In this case, the unit that the solver is using is Pascal, so be careful with the units when you're doing that. And then just same load center, and then similar distance away from the embankment. So after that, once we've done that, so we are going to check that the data is right. We reanalyze, save with a new, we save with a new name, and then we close the model, and that's what we are going to be doing right now. So I go back to my Excel file, and we you can see the input and the output. So that input doesn't change, is our target file all the time. We just run that example in just a matter of a few seconds. We have created this new file. We just open it, and there we go. As no magic is what we've done. We've changed that original circle into a square, and it's got a similar pattern of deformation underneath it. And the reason is it has there's a few things in here, but basically we need to take into account the grid refinement, which in this case it's every few meters, and then also it's a matter of how many rectangles were approximating the circle, as explained by Shiva earlier, because the polygons are approximated in that way. The more rectangles you use to define a polygon within that area of the polygon, then the more accurate is your response of the system. And I'm just going to close that one, which brings us to example 3. Conscious of the time, so I'm just going to run quickly on that one. I'll just go there and just go back to this. So in this case, instead of changing the loading, we are interested in changing the stiffness of one of the upper layers. In this case, is the made ground and also the London clay of our ground model. And what we do is just follow exactly the same thing. We go back to our example, and we just do exactly the same thing we've been doing, except that now we need to define a new soil profile, or you could also change in soil zones, but we're not doing that. Then what we do is creating a new profile, which is a copy of the previous one. And after that, what we do is modify and change those original stiffnesses, which for reference, if you've observed that we had 10 MPa for the made ground and 25 MPa for the London clay. We've halved those for this example. And then the soil profile, and that's important as well. Once you've created it in the code, you also want to assign it and make sure that that's the one running. So just to make sure that you get the response you were looking for. And just running that quickly, we can just click in there. Yeah, again, it just takes a few moments. And yeah, that's just created in there. And we can see, like happened earlier in some of the XDisp model. So the color scale has just broken slightly because of the update on the displacements. And once we fix that very quickly, we can see that it has doubled. So that's we had originally about 116 millimeters of vertical deflection, so the settlement, and now we are seeing 230, and that's what we can see in here, and it's just as a result of that halving the original stiffnesses. Right, so I'll just go to the fourth example in which building on complexity again on what we've done. So the difference in here is that we are trying to do, instead of going in and out of the model manually, setting a loop in which we are halving those stiffnesses in 3 steps. So original, half, and then half again, and that adds into the shape of, it adds a counter in the iteration. And the code is very similar in the first parts, and I'm just going to run through quickly on this. But the model basically checks the method chosen, if it's Mindlin or Businesque. In this case, we don't have any consolidation going. Then what we do is create again that copy of the new soil zone, and we need to call those stratums that are going to be changed as part of these iterations. And then what we do is within each iteration, we call those materials, we change them, and then we reanalyze the model. And we are going to do that checking the results that would happen for iteration 2 and then iteration 3, where we are halving those values of stiffnesses. And then we need to define more variables, because what we want to do is to plot in Excel or show in Excel those values which are going to be outputting from the model in each of the iterations. And then we can control that maximum settlement we are getting either on the points, lines, polylines, or grids. So the code is relatively similar, and again, it checks if you're using one or other solution, which is either it's Mindlin or Businesque, and basically goes through each of the points of the lines, the polylines or the grids, and it updates or resets the maximum displacement as long going through the results. And yes, then we are declaring those values and refer back to the Excel file, and then we just close the value. So I'm going to set that going. And then in the background, because it will take a minute or so, you can see this is now empty there. I've got some of the results there, but I'm just going to click on the example 4. And yes, I'm just going to go back to the presentation. I'll just wait for few seconds until the first result comes out, and then we'll move on to that. And then yeah, we can go on to some questions. Just show you that in the meantime. once it plots the first set of results, where you can see that there we go. There's the first line. So for the first iteration, where we've got the full original stiffness, we are getting about 77 mil on the points, which is on the center of the domain. It would be around under the embankment. The lines is around. It's on the surface or the crown of the. In this case, is the crown of the tunnel or the sewer alignment. We have no polylines in the domain, so basically there you can see we get 0 from the screening of the output results, and then we can just see that it's plotting the maximum settlement on the back of it, and that's where we go, and it's doubling because we're reducing by half the stiffness on each of the iterations, and that. Just leave it a few more seconds until it finishes, and I'll go back to the presentation. There we go, and that's the end of it. Right, I'll just go then. So what can we do with this? Somehow you could say the only limit is your imagination, but probably not, as is what the software can do. And it's really up to you how can you use for your benefit on your projects and your workflows. You can get more information on previous webinars that you've got the link in there, and also the manuals. And that's the end of it. So back to you, Mark, and thanks for your attention.
Thanks, Raul. That's brilliant. So yeah, hopefully we've given you a good overview there of PDisp and XDisp and some of the potential in terms of using them together and using them from your own programming routines, your own automations as part of wider workflows. That was the intention. So yeah, are there any questions on any of the things that were covered? Either shout out, or I guess you put them in the chat as well. Might be able to see those. Shiva had to drop off. It is a little later where they are in different time zones. But no immediate questions. We obviously we can take any afterwards if you want to drop us an email or anything. Alistair, I don't know if you have any.
Yep, I do have some closing slides to
Fantastic
for future events, but thank you to Oasis and Arup for the very informative presentation, especially on the VBA side, which is something I need to scratch up on myself. I do have some slides which I'll share now. Oh, it's showing the wrong. I think that's showing the wrong screen.
There's a couple of questions coming in the chat, Alistair.
Okay, we can go back to the questions.
It's just so can people ask questions via audio, or is it muted?
They should be able to unmute themselves.
Is that Isaac? And the second question is this session recorded? Yes. Yeah, I believe it is.
Yes, the session is recorded.
Perfect.
Hello, can you hear me?
Yes.
Okay. Yeah. Thank you. Here is Isaac Moya from IESA. Just have a couple of questions regarding XDisp. We've been using the program for modeling different excavations for some projects, and we've encountered some difficulties in some areas. But my main question was, well, in some projects that have some complex geometries, when considering, for example, different embedded wall excavations, like, I don't know, carrying cover, open cut, shafts, all at the same time. How can we deal with ground movements overlapping when using adjacent polygons, or how can we deal with re-entering corners with complex geometries?
A good
So
question.
that would be the question.
I know that is Vikram's area of expertise. I don't know if you want to able to answer that, Vikram.
Yeah, actually, in some cases, I think we can actually avoid overlapping effects to some extent. I think there are some controls in the program which I can send some examples offline. Like if I have your email, there are like corner stiffening effects and stuff like that, which are extended to re-entrant corners as well, which is what I mean, if it is something that you are looking for. So in that area, definitely, I think we can provide you some examples on overcoming such issues. It will be also more helpful if you can share some typical examples where you are encountering those problems. Like if we have a look at the geometry, I think we'll have more clarity on the type of problem that you are facing, and I think we can come up with something. Yeah, okay, I got your email. Yeah, thanks for that. Yeah, okay.
Thank you very much. I have another question, if I may.
Yep.
Okay.
Yeah.
So we also use the function for importing displacements from another source. So the question is, when importing displacements, is there any way to make XDisp interpolate between nodes with the information from those imposed displacements if those nodes do not match with the defined elements in XDisp, like grades, lines, etc.?
I think at the moment we don't have that interpolation feature, but I think probably Carol, sorry, I think Mark, I think this is something that we have in mind in future, but right now I think it's up to the user to get define additional points to make sure that there is matching. So right now there is no interpolation if you import grid point directly. Are you referring to grid points or lines?
Well, both. For example, we had a problem when we had defined some lines for assessing utilities, and we were imposing displacements combined with other programs. So when importing those displacements to the grid, then the displacements were not written in the utilities, in the lines in there, because the nodes there didn't match with the nodes of the imposed displacements in the grid.
Okay, with grids, I think there's a bit of issue. Like right now, we don't support like grid interpolation, but for lines, I think there is some utility. I think you can interpolate a bit. My colleague Shiva would have some information on that, so we will try to get this to you on how to do that, at least for the lines in the first instance. Then
It's,
also on grids also we'll get back to you.
I'll just
Okay,
add, it's
thank you very
certainly
much.
something we're looking to improve, because we've had feedback from a couple of people that it could be something that would, made a lot easier. For example, if you bring in a displacement field from GIS and you want to make that process easier, so it's very high on the list of things to look at.
Very nice. Thank you very much.
Are there any other questions?
Hello, everyone. Thank you very much for your presentation. My name is Francisco Marques from AKT2. I have a question regarding to GMAs and the use of XDisps. So basically, we use a lot of XDisp to do several GMAs on utilities here in London, like for example, Thames Water, gas utilities, etc. And one of the things we usually bump is that when we use XDisp, we carry out the impact assessment. Even if we try to put a very refined grid, or even with our best intentions, there's always like spikes in the, let's say, if you imagine like a strain curve and you have a certain limit that, for example, Thames Water specify limits for the utilities, and sometimes there are spikes because of numerical issues that that cause that value to pass the limits. And most of the ways to overcome this is to perform a smoothing exercise, which is one of the requirements of Thames Water for us to do that. Of course, within reasonable engineering judgment. So the way we do this, usually we have to export this data from XDisp out, and then we have to smooth, either use Excel or Python scripts or whatever, and then import it again to XDisp to rerun the new impact assessment, right, with these smooth values, and then prove to the utility owners that everything is fine. So I'm just wondering, are you guys planning in the future to put in XDisp any tool to perform that smoothing inbuilt on the program instead of the user have to export and import again? Because most of the times when we are dealing with large projects, it's already a lot of runs that we have to do, right? If we still have to import, export and import, it just make the process more tedious and more, let's say, prone to error from the user. It's just wondering if you guys ever thought about this, or if you have plans to implement something like that.
Thanks, Francisco. Oh, yeah, over to you, Graham.
Actually, we did have some feature for smoothing the displacement profile already. That is relating to embedded wall equations. But if it is coming from other sources as well, I think we will have to look at that. And again, I think if you can send us some sample models where you have some such typical difficulties, it will help us to come up with some solutions to overcome such issues.
Okay, thank you very much.
It's great feedback. Always good to hear of those sorts of suggestions. Fantastic.
Yeah.
If that's it for questions, I'll just go on to my closeout slides for upcoming events. So next week on the 17th, the BGA are hosting the 60th Rankin Lecture titled The Unusual and the Unexpected in Geotechnical Engineering, Observation, Analogy and Experiment by Professor Stephen Jafferis of Environmental Geotechnics Limited. That will be held at Imperial College in the Sherfield building from 5:30 to 7:30. Booking is required for that, which you can do so on the BGA website. Following that, the Early Careers group is having a networking event at the nearby Eastside Restaurant and Bar, which is sponsored by Mark McDonald and GCG. The day after that, the BTSYM are hosting another workshop, this time on tunneling in rock using drilling and blasting method by Mehdi Hosseini of LBA. This is in person at the IC from 3 to 5:30. Booking again is required. It won't be streamed. Shortly following that event on the same day at the IC again, there's the BTS evening lecture on the design and construction of a cavern in downtown LA by Carlos Herranz of McDonald's, which will include, as part of it, a detailed look into seismic analysis required for structures in that part of the world. This is at 6 o'clock next week in person, but it will also be streamed on the BTS YouTube channel. The BGA-ECG North are hosting a early career seminar at the University of Nottingham on the 23rd of March. There will be 2 postdoctoral presentations, as well as a PhD poster presentation and networking afterwards. This is from 2 o'clock in the afternoon till 6. Again, advanced bookings required. The BTSYM conference is going to be held on the 20th of May this year. We've recently extended our call for presentations until the 1st of April. Please apply through either through the link shown on the screen now or through on the website. Further details on the website, or if you're on a mailing list, we sent out the emails. The Doug Allenby Medal 2022 is a new initiative launched this year in memory of the late Doug Allenby. This medal will be awarded to members of the tunneling and underground space industry having up to 10 years of experience for making a significant contribution to project, team, or the industry. Again, we've extended the deadline for this to April the 1st. And I think that's it. So thank you to Oasis for hosting today's presentation, and thank you for everyone for attending.
Thanks for having us. Thanks a lot.
Indeed. Thank you. Thank you, everyone.
Thank you. Thank you.
Thank you. Bye.